Welcome back to CS520. Today I'm going to talk about the assembly process, the process of translating human-readable assembly language into machine-readable machine language. I'm going to do this by working on an example assembling a vm520 program. First, let's talk about the assembly process itself before we dive into that example. Again, it's translating human-readable programs into machine-readable programs. The key thing is it's structured as two passes over the input. The first pass is to determine the addresses for all the labels and store those in a symbol table. So a symbol table will contain these label address pairs. Then on the second pass, we'll generate the machine code. I'll also refer to machine code as object code. So why two passes? Well, it's because there can be a use of a label before it's defined. So we might see a jump to a label down further in the program. I don't know that address for that label yet because I haven't seen it. So the problem really is this problem of forward reference. So on the first pass, I just locate the definition of all the labels, store those in a symbol table, and on the second pass, there's no surprises. I'll know where everything is and I can go ahead and encode the instructions. Okay, let's go back to our example program that we looked at last time when we were learning about these assembly language programs. And I'm going to basically be filling in three different things. On pass one, I'll be computing the address of every instruction or directive that I come to. When I see a label, I will record in the symbol table the label and its address. And on pass two, we'll actually go through and encode each individual word. Okay. So the first thing is the assembler is going to, in this program anyways, the first thing is the assembler is going to skip over these comments. And the comments are just discarded. Last time I didn't talk about these export directives. Again, they're not executable at runtime. They are directives to the assembler. Basically, these are telling the assembler to publicize these labels into the output file, the object code file. On pass one, they're just going to be skipped. So we'll talk about them a little bit on pass two, and then we'll talk later about the actual encoding of the program into an object file. We'll come back to those export statements at that point. So the first real thing the assembler is going to process on pass one is this instruction. Again, the assembler assumes the program it's assembling will start at address 0. So this is the first piece of the program that's going to be represented as bits, and so it's going to go in the first slot, which is slot 0. And I don't have to do anything else on this program. I'm just counting things off basically. Next thing I see is the label sum. It's going to label what follows it, which is this word. And that will be at address 1. So now I'm going to record something in the symbol table. This is, again, a label definition of sum, and it's labeling the word at address 1. So I'll enter a pair in here. Sum is at address 1. Record that for use on pass 2. Next thing I see will be at address 2. It's similar. There's a label definition for length, so I'll record in the symbol table that length is address 2. Okay. Next thing will be at address 3. It's very similar. It's the label definition for vector. So again, I will enter vector address 3 into the symbol table. The next few things, I'm just counting off the words that are consumed. There's no label definitions, so I'm just counting the words as they go by. Remember, everything is one word in this machine. Of course, the instructions are all one word, and these one-word directives to the assembler correspond to one word being output into the object code file. That brings us to the definitions for skip data and the load immediate instruction at address 8. So again, skip data is being defined, so I'll enter a pair in the symbol table to track that skip data is at address 8. Now I have a bunch of instructions with no labels, so they're just counted off: 9, 10, 11, 12. I guess at this point it's become apparent I'm using decimal for these addresses here. That brings us to address 13, which is labeling this instruction, and there is a label definition associated with that. Top is at address 13. Again, that's in decimal. So my symbol table addresses are also in decimal. And I have some more instructions without any labels, so those are going to be counted off. They each consume one word. Come down here to address 19. I see a label definition for done. Done is at address 19. And that brings us to the last thing in the input, which is at address 20, the halt instruction. No label being defined, so nothing to be added to the symbol table. So that concludes pass 1. And the key thing again is I made these 6 entries into the symbol table tracking labels and their addresses. So now I come back around, read the input again, skip over the comments. I come to these exports, and I'm going to note that I saw them by updating my symbol table just to reflect that sum was exported, top was exported, and done was exported. Again, we'll come back to this when we go to generate the object code file. But I'll just note that those 3 labels were exported, the other 3 were not. At least they haven't been yet. Okay, that brings me to the jump instruction. At this point now I'm going to dive into encoding these instructions, and you may want to have handy the documents that are available on the web that provide this level of detail. For in particular, if we look at the jump instruction description in the corresponding document, again this document's linked from the course web page, it shows me the format, that it's jump followed by the address, and that the opcode itself is encoded with hex 14. Okay. And then I need to consult the format document. When I have an opcode and an address, the opcode goes in the bottom bits, there'll be 0 in this unused space, and then the address will be the top 20 bits. At this point I think I can encode this instruction. The jump will have the opcode of 14 down in the low order bits. It has an unused spot for 0, and now I have to calculate what address do I want to store in the instruction for skip data. I can look skip data up in the symbol table and see that it's at address 8, but now I have to remember that the machine uses PC relative addresses, and I'm actually going to have to do a calculation here so I figure out what address field to fill in. That's a little bit tricky actually, because what happens is if we go back and look at the jump instruction one more time, let's look at the actual operation. The actual operation is down here. It's going to take the address from the address field of the instruction and add it to the program counter. That's how a jump is implemented, right? I don't want to execute the next instruction in line. I want to jump somewhere else in the program. So I want to change the PC from the default of just incrementing it. The tricky part though here is I've got to remember how the fetch execute cycle works. Now let me just remind you. For this machine, the fetch execute cycle starts with fetch the instruction at the address given by the PC, then it increments the PC, then it executes the instruction. So in fact, the PC has been incremented before we execute the instruction. So the PC will not point to the current instruction, it'll point to the next instruction when we're doing this addition. That's the tricky part. Okay, so let's do this carefully. Basically, I have the new PC I want is going to be the current PC plus what I have in the address field. Well, I know skip data. I know the address I want. Skip data, I looked in the symbol table and I found out it was 8. So I want the next instruction to be fetched to be at address 8. So this is 8. What's the current PC? Well, the instruction itself is at address 0. The instruction that we're executing right, thinking about executing in the future actually, is at address 0. But remember, the fetch execute cycle will have incremented that to 1 prior to us executing the jump instruction. So what I want to store in the instruction actually is 7 in order to be able to add 7 to the 1 and get the 8. So I'm going to have a 7 placed into that 20-bit address field in that instruction. So that's the encoding of the first instruction. Okay, let's go to the next instruction. Well, it's not an instruction, it's just a directive to the assembler to put out a word filled with zeros, right, whose value is 0. Notice we don't care about the label definitions on this pass. We've already processed them on the first pass. Next one is similar. It's just a word with 5 in it. Note, I'm representing the contents using hex. So in fact, I can do all these pretty quickly, right? These are all just definitions of words to be placed into the memory of the values 1 through 5 in order. So the assembler will fill in those words. Okay, now I come to skip data itself. Again, I don't really care about that label. Now what I care about is encoding the load immediate instruction. Load immediate instruction's opcode is 03. I can look it up and see that. The next thing in the instruction is going to be the register. Again, let me just show one more of these. I'm going to probably stop doing this soon, but the load immediate is a register and a constant. It's this format here. So the opcode will go here, the register, and the constant will be in the upper bits. So in this case, the register is 0, so I'm putting a 0 in, and in fact the value of the constant is 0, so all these upper bits are 0 too. Notice at this point you can see that the bits themselves can't tell you whether it's an instruction or a piece of data. Here's a word with 00000003 in it. Here's another word with the exact same contents. This one is piece of data. This one is instructions. So somebody has to provide an interpretation to the machine so it knows what's going on. In this case, we'll execute this word. In this case, we'll compute, we'll pick up this word and load it into a register. So the bits themselves won't tell you what's actually in there. Okay, how about the load instruction? Load instruction, the opcode is 01. It has a register spec, which is 1. And the upper 20 bits are going to be the address, the PC relative address for length. So again, I've got to do a little bit of arithmetic here. I've got the same formula again. I want the It's not the PC this time. It's the Operand address has to be the current PC plus an address. And the address of the instruction we're encoding is 9, but that will be incremented to 10. So we know the current PC is 10. What's the address of length? Now we have to consult the symbol table. Symbol table tells me the address of length is 2. So what I'm trying to compute here is an operand address of 2. So in fact I need to have -8 in the address field. Okay, so I got to do a little bit more work. I have to come up with a 2's complement representation of -8. So 8 is 0. If I do it in 8 bits first, it's this, I guess, right? And I know I complement it. I add 1. Okay, and I need to drop that into a 20-bit field. I'm going to extend out with a bunch of 1s. So the 20-bit constant is going to be F, 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 8. So I fill that in here. F, 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 8. Alright, so make sure you understand that. If that doesn't seem to make sense, then raise questions on Piazza or bring them to recitation. Got a similar thing. I have to do a load address R2 into vector. What's the opcode for load address? 04. Register being referenced is 2. And I'm going to have to compute another similar calculation to the one I just did. Right? I'm going to have to, the operand address, the operand equals the current PC plus this address field that I'm trying to figure out. So I need to look up, the operand is vector, look up vector in the symbol table, it's at address 3. The current PC will be 1 more than the address of the word I'm encoding, that's 11, plus address. So again, address needs to be -8. That makes my life easier because I already know what -8 looks like. It's F, 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 8. Okay, then I come to a load immediate R3 constant 0. So this is similar to what I've done before. Load immediate is opcode 03. This time I'm loading register 3. And the constant again is 0 like it was before up here. It's just the register spec has changed. And again, another similar instruction. Load immediate is opcode 03. The register being set this time is 4. And the value is 1. So in hex, it's that. Let me get rid of this piece of paper. It may be distracting you with that calculation there. Let's go to the next instruction. Okay, branch equals with 2 registers in it. I think I better consult my format document to figure out how that works. Branch equal 2 registers and an address. That's this bottom one, I guess. Opcode 2 registers and an address. So opcode of the bottom bits as always, then the first register spec, which is the leftmost one in the human readable form, and then the second register, and then now the address is only 16 bits. So branch equal, the opcode is encoded as in hex is 1-3. Then this leftmost register gets encoded here as 0. The next to the right gets encoded here as 1. And again, I'm going to have to do some math here to compute the PC relative address for done. So I'm doing a branch instruction, so we're talking about setting the PC. New PC equals the current PC plus the address, what I'm trying to compute. Current PC will be one more than the address of the instruction I'm encoding, so that's 1-4. I'm trying to get to done. I got to consult the symbol table for done. It's 19. Now in this case I want an address of 5. And it's a 16-bit address, so it's these 4 hex digits. Alright. Another tricky encoding situation. Load indirect R5 with an offset of 0 off of where R2 points. Again, remember what this instruction means is R2 is essentially pointing into memory. I can adjust that pointer by adding this offset to it. That's where I'm going to, the address that results from the addition of 0 to R2 will be where I load the operand from, and I put it into register 5. Let's again consult the encoding document. That's format 7 here. Opcode, leftmost register in the human readable form. Then the other register next, and finally the offset in the upper 16 bits. Okay, so load indirect is opcode 5. Then it's going to be register 5. And then this register, register 2, and then a 0 offset, which means these upper 4 hex digits are zeros. I got a whole string of add and integer instructions, R3, R5. Add instruction is 0B is the offset. Sorry, is the opcode. 0B is the opcode. Leftmost register will go here. Rightmost register will go here. And these are all zeros. It's unused in this format. These are all going to be very similar. They're all, the next two instructions here, they're both add integer, so they're both B's, 0B. This one is referencing R2, this one is referencing R0, and these are both R4, and the top part of the instruction is unused. Alright, now I come to a jump instruction to the top. And we've done a jump instruction before. It was the first instruction we did. The opcode was 1-4. The register portion is unused, so we put a 0 in there. Now I have to compute the address of top. Look in the symbol table. Top is address 13. So again, I want my new PC to be 13. My current PC is going to be one more than 18. So that's 19. So my address is going to be another -1, it's going to be -6. So I've got to compute -6. What's the 2's complement representation of -6? Well, there's 6 and 4 bits. I flip the bits. Whoops, I flip the bits and add 1. So it is 1 0 1 0. I sign extend out as far as I need to go. In this case, it's a 5 hex digits for the address. So that's going to be F, 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 and what's this? A. So back to encoding the instruction in F, 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 A. Okay, we're getting near the end. Store instruction. Opcode is 02. The register is 3. I have to compute the address of sum. So the operand address plus the current, equals the current PC plus some address field, which we need to compute. So the operand address for sum, I got to consult the symbol table. Sum is at address 1. So I want this to be 1. The current PC is going to be 1 more than 19. That's 20 plus address. So my address needs to be minus 19. Alright, let me represent 19 in binary. That's a 16 and a 3. Do it in 8 bits initially. Again, I complement the bits, add 1. And I sign extend with 1s to fill up the field. In this case, again, it's 20 bits. So it's going to be F, 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 E, what's that? D, I guess. So the address field now, I can fill in F, 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 E, D. Okay, that brings me to the last instruction, which is the halt instruction. It's the format where there's only an opcode. That's format number 1 here. So the opcode goes in the bottom bits, and then everything above it is 0. So that's pretty easy. And in fact, the opcode for halt is 0 also. So the last word in the program is all zeros. So that's pass 2 then. We know the contents. We've filled everything in. What happens next? Well, we have to put this encoded program into a file so it can be stored in the file system and referenced later. So that file is usually called an object file or an object code file. Let's take a look at that kind of generically first of all. These are the .o files that you see when you compile your C or C++ programs. So these files contain machine code and associated symbol information. We understand the machine code. What's the symbol information actually? Symbol information is, there's basically 2 kinds of symbols that are being kept track of. What I call end symbols. There's labels defined in the machine code, and they're going to be exported to the linker. I'll talk about that in just a moment. Let me talk about the other one. Out symbols are labels referenced in the machine code but not defined in the machine code. So the program we just saw had no out symbols. Everything, all the labels I referenced, I was able to find them in my symbol table. But consider the case where you're writing a C program and you call printf. Right? You don't write printf. You don't provide a definition for printf. You expect a piece of code called a linker to run later and combine code that somebody else wrote for printf with your C code. Well, printf is an out symbol in my terminology. We would see in the assembly language, we would see a reference to printf, but we wouldn't find it in our symbol table. So we need to record that into the output file with the hope that the linker will come along later and combine object files together, matching out symbols in one file to in symbols in the other file. Because you see, printf will be an in symbol in the file that's pulled from the standard C library. It will be defined. The linker is basically matching up out symbols with in symbols in other files and then combining the code all together in one big program. So we need to leave information around about the in symbols that were defined in our machine code and that were exported to the linker. We might not want to export everything to the linker. That's what those export directives are all about. And we also need, of course, to tell the linker about our problems. That these are holes really in our code. We don't know what addresses we need to fill in. We need some help. The linker will provide that help. And we'll have a separate lecture on linking later when I'll go through the details of how the linker actually works. Okay. What's the actual structure of this file in the vm520 world? Well, in vm520, an object file is just a series of 32-bit words stored in Little Endian format. If we look at these words, structure is relatively simple. The file starts with 3 words. Each one is the length of a corresponding section in the file. There's only 3 sections. So there's an in symbol section where we record the in symbols, an out symbol section where we record the out symbols, and then the object code or the machine code itself. And the 3 header words here just tell us the length in words, so the units of words of these sections. Tricky part is how symbols are represented in these sections. Let me look at that next. Each symbol in either this in symbol table or the out symbol table is stored in 5 consecutive words. In words 1 through 4, the ASCII for the name is actually encoded in those 4 words. So what's that? Those are 32-bit words. So we have a maximum of 16 characters in our names that are publicized in the in symbol or out symbol section. And then word 5 is the address. And the address has 2 different meanings. For an in symbol, it's the actual definition address where that label was defined. For an out symbol, it's the address of a reference. What do I mean by a reference? Well, it's the address of the instruction that's actually referencing the symbol. So it's the address of a jump instruction, for instance. It's jumping to some symbol that we don't know the address of yet. What this means is that a symbol can appear more than once in an out symbol section. Going back to your C program that's calling printf, if you called printf 4 times, you would find 4 out symbol references. 1 for each instruction that actually referenced that symbol printf. Maybe I should go back to this word address that I put these 2 asterisks by, and I'm assuming that these addresses are now relative to the beginning of the file, where the beginning of file is assumed to be at address 0. So if the in symbol was defined as the first word in the file, it would have address 0 in the in symbol section. This example shows you how the names are packed into the 4 words. If the in symbol is done, is the ASCII string DONE, and the address is 19 in decimal, what are we going to see actually in the words? Well, we'll see that the first byte of the string is put in the low bits of the word, of the first word, and then the next byte, and it wraps around like this. In this case, I've only got 4 characters so they all fit in the first word, and then I zero fill or null fill the other 3 words. Finally, the 5th word is the address, and of course I'm representing it in hex here. So address 19 in decimal is 13 in hex. So this would be the end symbol record, I may call it, for done at address 19. This is how it would look in the file. Okay. Well, I probably bored you enough already, so I won't go through all the details of encoding the actual file, but let me just quickly show you an OD dump of that file. This is an OD dump. I'm using TX4, so I'm gathering together 32-bit words rather than individual bytes. That's what that argument to OD means. Looking at this sum vector OBJ file, again, remember the left column here, leftmost column is just the starting offset of the first word on the line. So that's not really in the file. So the first 3 words would be right here. It's telling me that the end symbol section has 15 words in it. Divide 15 by 5, that means there's 3 end symbols in there. And why are there 3? Well, those are the 3 exported symbols in the program. Right, I'm going to see an end symbol record for each of those exported symbols that were defined in this file: sum, top, and done. Those are being publicized to the linker. There are no out symbols, as we noticed. I never had any holes. I always knew the address of all the labels that were being referenced. And then the object code takes up, what's this, 15 in hex, that would be 21 words. The object code itself is 21 words long. Does that make sense? Let's go back to our little sketch of the assembler's work. Yeah, there's addresses 0 through 20. So that's 21 words, because the first word started with address 0. So that makes sense as well. And here then is the end symbol record for done, as I showed it just a moment ago. Right, here's the word done, with the ASCII characters appearing right to left inside the word. A bunch of 0 fills in here. The address 13, which is 19 in decimal. And we see the next end symbol record here. This is for top, actually. T-O-P, 0 fills. The rest of this. The address is D. Okay, does that make sense? What was top? Top. The address was 13. That is D. Okay. And finally, here's the address for, the end symbol record for sum. S-U-M, 0 fill out here, and it was at address 1. Again, going back to the program, sum was at address 1. And finally, here are the encoded words, starting off with this 0007, 014, that's this, and ending down here with the FFFED 302, FFFED 302, and a 0 word for the halt instruction. So that shows you how that file would actually be encoded into an object file. So the original assembly language file is translated and encoded into this object file. Again, note that only exported symbols, if I go back and look at my symbol table, only exported symbols get placed into the end symbol section. So length, vector, and skip data, for whatever reason, the programmer did not publicize those to the linker, so they're not included in the end symbol section. Okay, well that was a reasonable amount of detail. Again, but shows you how to write an assembler for the vm520 system.